Good morning, everyone. Welcome to my presentation. Before I start this presentation, I would like to say a few words about myself. My name is Tata Fritsco Mabui, originally come from Indonesia and currently working as a research engineer for LKB at Kiruna Mine with the focus of mine ventilation related topic. As you can see on the screen, today's topic is about improving the simplified ventilation model for mine expansion planning at Kiruna Mine. So thus this presentation is structured as follows. First, I would like to begin with the introduction, which covers the general information about LKB, Kiruna Mine, as well as its primary ventilation system. Moving on to the next section, which deals with the background of the study, why we conducted this study in the first place. Also in this section, I will show you how the model looked like prior to the adjustment and how it looks like now. In the third section of this presentation, which is about procedure and progress example, I will show you how the adjustment helped us to increase the model accuracy. In addition to that, I will then present some data as a result. And finally, before I summarize the presentation, I will highlight some challenges concerning the inaccuracy and which work required to further enhance the model. At the end of this presentation, there will be 5-minute time for question where you are more than welcome to ask any question. So let's jump to the introduction part. As a major European producer of iron ore products, LKB is a Swedish state-owned company. We have 3 different operation sites, which called Svappavaara, Malmberget, and our focus today, Kiruna. They are situated above the Arctic Circle in the northern part of Sweden. As a company, we aim to achieve transformation towards critical minerals, carbon-free iron sponge, while contributing to the New World Standard for mine operation. So what you can see on the right side, the picture shows how the Kiruna mine looked like, which considered the world's largest underground iron ore mine. The ore body has length around 4 to 5 kilometers with a width of up to 120 meters. In this mine, sublevel caving is applied as an extraction method, with the current production is situated below level 1000 meters, and the main haulage is currently at the depth of 1365 meters. The production capacity is roughly 28 million tons per annum. So the picture on the right side illustrates how primary ventilation system works in Kiruna mine. We applied push and pull system and have around 14 fan stations. The total ventilation capacity of this station is around 2,500 cubic meters per second, and most of it can supply air around 150 cubic meters per second for one mining block, while the largest one, which has capacity up to 450 cubic meters per second, can supply 2 different mining blocks. Around 15% of those supplied air is delivered to the permanent infrastructure, while the other goes to production areas. So that was it about the brief introduction of Kiruna mine. Let's moving on to the next chapter, which I will give you a brief overview about how we updated the model. We can start with what was done previously. What you can see here is the picture of simplified ventilation model, which was used to study airflow requirements for the expansion and also for the optimization of the current ventilation system. Previously, simplified approach was used to perform this calibration, which I will talk in detail in the next slide. So what I mean by simplified approach can be described using these categories. What was the input for the model, what was included and what was not. As a main input, we use available information such as old CAD file references, as well as existing Ventsim model for some infrastructures. Furthermore, when performing the calibration, few parameters were used, mainly in use infrastructure, such as rams, ventilation shaft, to name a few, whereas production drifts, auxiliary fans, and ducts, etc., were not part of this calibration. The further information regarding the inputs and what was included and was not can be found in this slide presentation. As a result, for the first calibration, airflow in primary ventilation infrastructure was found to correlate within 10%. However, errors were still high, which caused a high discrepancy between measured and the model values due to the several reasons. First, leakages in the cave levels and from old ventilation shaft. And also, since the old CAD reference were not complete, there were still missing references which affect the airflow distribution in the model. For that reason, in order to apply the model usability for the study of the near future planning, it is important to improve the accuracy of the model. Hence, during this project, second calibration were performed. How it was done? So basically, we use previous model as an input and update it based on our more information and also according to our findings during the fieldworks. As I mentioned earlier, we put additional input to the previous model, which you can see on the left figures. And when performing second calibration, we basically included the previous parameter, which were excluded before, for example, old shafts and upper level connection. However, due to the limited resources, parameters such as production drifts, auxiliary fans, and ducts were still not part of this model calibration. So that leads us to our updated model, which is presented in this slide. As you can see, compared to the previous one, there are more airways available, especially in this part where the leakages were identified. Furthermore, the model has been adjusted to more or less match the actual underground situation. So now we have just finished the model building process and we move on to the next section. In this part of the presentation, I will show you how the adjustment helps to improve the model accuracy. First, I would like to begin with the model organizing, so how it was done. Basically, what we have done is just organize the airways according to their functionality. For example, assign the airways according to mining blocks or performing level separation, which you can see on the right side in different pictures. By doing this, it helps us to improve the usability of the model, and it's also make it easier when performing the fieldwork. Another thing that we have done is to performing site visit. By doing this, we try to confirm or to correct the inaccurate old references, thus reduce erroneous airflow distribution. And finally, by adding previously excluded old tunnel section, it will make the better representation of the current airflow circuits. So jumping to the next presentation regarding model improvement after the adjustment. Here what you can see, we have tried to improve the resistance values of the model and consequently correcting its airflow distribution. By doing this, we have added into the model different resistances based on what we have found during the fieldwork. You can see on the left side is the door, steel door, and you can also see that on the right side symbolize the walls. Moreover, we have actualized the tunnel profile to match the underground current situation and thus make the resistance value in the model better. So another thing what we have done was the model correction. We have realized that by adding some relevant parameters such as old shafts or old rams, it has lowered the model accuracy, which you can see on the upper right picture. So here's the old rams, here's the old shaft. Both of them show high airflow quantity, which doesn't match our underground condition. It can be fixed by applying resistance in this connection. However, due to the limited resources or information regarding the resistance types in this connection, or sometimes also lack of accessibility of this area. A subset needs to be made to correct this airflow. What we have actually done, we have applied what we have seen on the other part of the mine and tried to use it here. So to give you an example, here's how the typical connection looked like with the resistance type. So based on this information, we use the preset resistance value in Ventsim and apply it here. So as a result, you can also see in the right side, the airflow model was improved. So previously we have seen how the model has improved after adjustment. And now in this part of the presentation, I will present to you how the adjustment improved the airflow value in the model as well. So for that reason, we have taken several airflow measurements from the previous measurement points. The results were then compared between the previous and the updated model. Overall, improvement was observed, which is visualized in the graph here. However, despite of the improvement, the inaccuracy is still high, which is around 73%. But if we look in specific areas, significant improvement can be seen, which I will talk in detail in the next slide. So as I mentioned earlier, this slide will show you the area in the model with the significant improvement in terms of airflow value. This mentioned area is the connection between the mine and the main hoist, which show high flow in the previous model. From the previous graph, which can be seen here, this particular area is represented by those measurements, and the right side, the graph here, is the bigger version of those measurement points. As you can clearly see that the updated measurement point here is less erroneous compared to the previous one. So in other words, by adding the adjustment, we have improved the airflow value and managed to reduce the average erroneous up to 37% compared to the previous one. So in the last two slides, we have already seen that compared to previous model, the updated ventilation model shows better results after the adjustment. However, to get a better picture of the whole mine, further measurement points were taken as well and then compared. The result will be summarized with this graph. Overall, despite of some improvement, there is still big value gaps between measurement and the model. Let me break into the results based on the location in the mine. But before I start, I will just briefly show you which area in the mine those values were taken from. So just to remind you, here is the ventilation model after adjustment. So on the right part represent the north, while the left represent the south. And those areas here represent the upper level, and here's in the middle, and here's the lower part. So now we look what the graph tell us. First, we start with the lower sections. As you can see here, the erroneous is really high. It is due to the exclusion of the auxiliary fans, which are situated in this area. Moving on into the middle part. So in the middle, some measurement points show good result and some not. So the accuracy is actually affected by the continuous development because of the seismic event that happened a couple years ago. Similar level of inaccuracy also can be seen in the south. So the higher accuracy is still challenging to be achieved due to the ongoing development in this area. And for the upper parts, no conclusion has been made due to the lower number of taken data. So now we're going to the north, which is relevant for the future expansion towards the greater depths. So as can be seen here, so the model has shown better results with the erroneous below 50%. To conclude this, some areas show some significant improvement after adjustment. However, some areas still require more attention in order to improve the model airflow value. So now I'm approaching the end of this presentation, so let's recap what we have covered until now. From the previous slides, we managed to improve the model usability. However, overall inaccuracy is still high. So in this chapter, I will summarize what it was challenging at the time to reach higher accuracy of the model. So first, newly added main ventilation roads. It is a critical part of the modeling, which can affect the overall values if not modeled properly. And secondly, We rely on the information regarding blockage without confirming it, which possibly could lead to inadequate airflow distribution. And next, it is also recognized that absence of auxiliary fans was the main contributor for high value differences. Moreover, the assumed upper level section could bring the imbalance into the model as well. And finally, the time gap between the change in the infrastructure and the documentation can cause missing airways that leads into the inaccurate model. So the example you can also see in the right picture here. So that leads me to my next point, which is about what we can do to further strengthen the model. So first, of course, we need to include the auxiliary fans and the ducts as well. Another thing is that we need to evaluate a more accurate resistance value by performing pressure survey. Also, we need to take more detailed information from the upper level in order to model it properly. Furthermore, we need to continue to do the ventilation mapping to identify or to confirm the location of blockages for the proper airflow distribution in the model. And finally, continuation of the updating the airway is required. So to conclude this presentation, during this project, we have attempted to increase the model accuracy by performing the second calibration with the inclusion of more detailed parameter, example the old shaft, upper levels area, and the other previously excluded connection. We also adjusted the model based on our available information and through the findings during the fieldworks. It was observed that the usability of the model was improved. The model is now organized based on the functionality. Changes are available in the model. However, the overall discrepancy between the measured and the modeled airflow is still high. But improvement have been observed in some area, especially in the northern part. So, in order to further enhance the model, we still need to do more work for it. So that's it about my presentation. I believe there is always room for questions. Since I'm unfortunately not able to attend this presentation personally, I believe my colleagues Mr. Klose and Mrs. Martikainen can answer your questions. But if you like to get more information, you are more than welcome to contact me through the app WUFA, and I'm more than happy to answer your questions. Thank you so much. So once again, before I end this presentation, I would like to thank you for listening, and I hope you have a great day there. Thank you so much.
Thank you for recording the presentation, Tata. So as he said, we have two of his colleagues here to potentially answer questions. There's also the app where you can ask questions for the presentation or directly to him as well. So do we have any questions? Yes.
Very nice presentation. Just a quick question about auxiliary vent, which you have mentioned that you're concerned about. Just trying to figure out what aspects of auxiliary ventilation are you planning on adding to your model, which should help you in estimating your flow-through ventilation in a better way?
So far, we have only had the main fans included, so we feel that especially the secondary ventilation fans and the ducting we need for the production areas to get a better feel for what's happening there. However, we are going to leave comfort ventilation, which we have in some of our workshop areas, for example, away from this model still.
Thank you. Any other questions?
Yeah, thanks for the presentation. Just a quick question. There was a lot of talk about the accuracy of the airflows. How did you find that the accuracy of the pressures in the model changed? Because that's obviously what's driving the airflow.
That's our biggest challenge at the moment. We just do not have enough information from underground. We do not have the access to several of the areas to be able to take the pressure measurements, and we have felt that prior to getting at least all the required connections in place and having the real airway shapes, it's not sensible for us to start with the pressure surveys. So we are still working on that. Thank you.
Hello, got a bit of an easy one. Just with the scale of the mine, both by strike length and by depth, it seems as if this is a lot of work that had to get done. So within a 15-minute presentation, I don't think a lot of people can gain an appreciation for specifically the amount of effort that it probably takes to try calibrating a model of that size. But out of curiosity, how big is the team at the mine itself, and how long has this process been undergone for?
Well, those are very good questions. We actually got bits and pieces of this model put together by a consultant several years ago. But of course, there's been a lot going on since then. So we basically, a couple of years back, built the simplified version, just adding the main features in and trying to see if we are anywhere even in the ballpark to make use of the model for future planning. And we realized that, yeah, for future planning, we can use this in a limited manner, but to do anything shorter term, we have to improve the accuracy. We don't have many people working on this at the moment, only a few. So it's been a long road, and we foresee this still taking quite a long time before we are where we want to get to. And that is to actually give the model from the research group side to the operational side to the mine. Thank you.
Any other questions? Yes.
Thank you. Not really a question, but a contribution. We have been through such modeling, 8 kilometer strike length and 1.6 meter deep. And it's quite difficult, appreciating how difficult it is. And we had to block the mine airways, cut it off to a simplified version so that you could measure the pressure and the quantity, then open it up gradually. So in our case, that is how we started, to simplify it at one mining area, and then you open it up gradually so that but it involves building a lot of vent walls to close up the mine. Thank you.
That's a very good comment. Thank you very much for that. That might help us further.
Thank you. I think that's enough questions. If there's any further question, don't hesitate to use the app and ask them through there.